Welcome to this video. So in this lesson, we are going to look at the hypothesis testing using a t-test. Okay, so to any hypothesis procedure, okay, there are basically 5 steps that are involved. Okay, so the first one is writing the null hypothesis, okay, the null and the alternative hypothesis. Okay, so that's the first step. Once you identify your null and um, the alternative hypothesis, okay, you have to identify what we call as your test statistic. Okay, so here is where you ask yourself, am I going to use the Z test? Am I going to use the T test? Okay, so usually if the sample size, okay, is less than 30, we use the T test. Okay, and if it's greater than or equal to 30, we use the Z test. Okay, but that also has some restrictions. So you look at if the population standard deviation has been given or not. So if it has not been given, then we have to use the T test. If it has been given, okay, then we'll use the what? The Z test. Right, so this is the second step. The third step is determining the critical value. Okay, based on these hypotheses that you are going to come about. Okay, you have to determine the critical value. So if it's a one-tailed test, then it will either be positive or negative. But if it's a two-tailed test, okay, then you have a negative one and a negative one. So come up with a critical value. And then the fourth step, okay, is to make the decision. Okay, so based on the calculated test statistics, okay, and the critical value that you found, you have to make a decision, and then finally you have to conclude, okay, either to reject the null hypothesis or to fail to reject the null hypothesis. All right, so depending on what your alternative hypothesis is, okay, it's going to tell you either you have what we call as the one-tailed test or a two-tailed test. Okay, so the null hypothesis indicated by HO, okay, should always include an equal sign. Okay, so let's say the mean is equal to maybe 0, okay, and then the alternative hypothesis, okay, it can be that mean is not equal to 0, okay, or it can be that the mean is greater than 0, or it can be, okay, that the mean is actually less than 0, okay? And then this null hypothesis, it can also be that the mean is greater than or equal to what? To 0, okay? So in the null hypothesis, there should always be a what? An equal sign, okay? If there's no equal sign, then we can't call that as the null hypothesis. So now I was saying, depending on what your alternative hypothesis is stating, you are going to come up with a one-tailed test or two-tailed test. So this one here, they're saying the mean is not equal to 0. Okay, so meaning this test can go to the right side and it can also go to the what? To the left side. So we're going to say that that one is a two-tailed test. So if I, for example, I have this as my distribution, okay, and then I have some rejection region here, and then I also have some rejection region there. Okay, so we are going to have a two-tailed test if we have two rejection region. So this situation happens if we have an alternative hypothesis such as this one. Okay, and then for this one and this one, okay, I'll draw the one for the greater than. It will be like this. Since they've said mean is greater than this value, okay, then the rejection region should be somewhere there. Okay, since they've said this one is greater than, okay, so we are going to be getting positive values here. Okay, if it is less than like this one here, it means the rejection region will be going to the left like that. So, or the values that are falling in this region will be rejected. All the values that are falling in that region will also be what? Rejected. So depending on the alternative hypothesis, we know that if we're going to have a two-tailed test or a one-tailed test. Okay, but for the questions that are in this video, I've made them very simple so that we just get the basics. Okay, so let's read the question here. So they're saying um, a new drug is tested on 12 patients. The post-treatment systolic blood pressures have a sample mean of 133 millimeters of mercury and a standard deviation of what? 8 millimeters of mercury. So here they've said a sample mean and the sample standard deviation. Okay, so meaning, and then we also look at the size. Okay, so the size is 12. Okay, the sample mean, okay, has been given as um, 133. Okay, and then the sample standard deviation. Okay, the sample standard deviation indicated by S has been given by 8. Okay, so one, the size is small, okay, and no population standard deviation has been given. So it means here we use the what? The t-test. Okay, but is it going to be a two-tailed or one-tailed? Okay, so let's read the question. So they're saying test at significant level of 0.05, whether the drug lowers the mean systolic blood pressure below the non-standard treatment of what? 140. So it means here, okay, let's write our hypothesis. So step one, write the hypothesis. So the now hypothesis here is that the mean, okay, is equal to what? To 140. And then we're testing to see if this mean is lowered. So we are saying now the mean should be less than what? 140. So this is a one-tailed test to the left. Okay, so if I draw my distribution like this, it means I'll have to find a value of t somewhere here, such that wherever comes before this value of t, this one here, to be the rejection region. Okay, and then whatever value of t I'm going to calculate from the table. Okay, since this mean is less than, is going to be negative here. Okay, so this is our hypothesis. So our test statistics is that t calculated, okay, t calculated is equals to the sample mean minus, okay, the population mean, and then divided by the sample standard deviation over the square root of what? The sample size. Okay, so let's calculate this one here. So t calculated will be equals to sample mean is 133 minus 140 divided by 8 square root of 12. Okay, so when I evaluate this, I get approximately minus 3.03. Okay, so this is my t statistics that I've calculated. Okay, what about the t at the critical values? Okay, so the t at the critical values is given by, okay, it's given by t alpha and then degrees of what? Freedom. So the degrees of freedom are given by the sample size, which is 12 minus 1. So this will be 11. And then this here, okay, you just get whatever you have here. So it will be t 0.05, comma what? 11. So we don't divide this one by 2 here because we said this is a one-tailed test. Okay, so we leave it the way it is. Okay, so we want to find the value of this one. So we go on the t table to look for t 0.05, 11. Okay, so t 0.05, 11, where is it? Okay, so 0.05 it's here, and then I have to go where 11 is. So 11 is there. Okay, so the value is this one here. So 1.796. Okay, but since it's a left-tailed test, okay, we're going to write it as a negative here, minus 1.796. 6. So now, okay, for us to reject or not reject the null or fail to reject the null hypothesis, we have to compare this t calculated, okay, to the t at the critical value. Okay, so remember the shape is like this. So this t here is here. So t is equals to minus 1.796. Okay, so the rejection region is this one here. So if the value that I've calculated is in the rejection region here, we're going to reject this null hypothesis. Okay, but if it's more than this one, we're not going to reject, because all this region here, we are what? Accepting. I mean, we are failing to reject this language. We're not accepting, but we are failing to reject. Fail to reject region, this one here. Okay. Then here we're going to do what? To reject. So now let's compare this value and this value. What do we see? Okay. We see that the calculated value minus 3.03 is actually less than the critical value. So what does this mean? It means this value falls in this region here. So since it falls in this region, okay, since it falls in this region, we are going to reject the null hypothesis, this one here, okay? So what will be our conclusion? Okay, so we are going to say reject the null hypothesis, okay? We can just write reject OH, okay? And then conclude that at, okay, significant level 0.05, okay, there is enough or sufficient evidence, okay, to conclude that the new drug lowers the mean systolic blood pressure. Okay, blood pressure like that. Okay, so we have rejected this null hypothesis here. So it means this one here is the one that we're going to consider. So reject HO. Okay, then it means that at 0.05 significant level, there's enough or sufficient evidence to conclude that the new drug lowers the mean systolic what? Blood pressure. All right, let's look at another question here. Okay, so we're still doing the t-tests. So here they're saying after a novel iron supplement regimen, 10 patients, okay, so my N is 10, with iron deficiency anemia have mean, okay, hemoglobin 11.2 and the standard deviation 1.5. Okay, test at 1% significant level. So 1% significant level, it means my level is what? 1/100, which will be 0.01. Okay, so test at 0.01 significance level, whether this mean differs from the normal population mean of this. So these are keywords, differs, okay? So it means our now hypothesis will be that the mean is equal to this guy here, 13.5. Our alternative hypothesis, okay, will be that the mean is not equal to this guy. Okay, so it didn't say lower here or higher. They just said differs. So meaning it can be higher or it can be lower. No wonder we are writing this in our what? In our alternative hypothesis. So what does this mean? Okay, it means we have a two failed tests. Okay, so if I have my distribution here, okay, so it means the statistics that I'm going to find, I'm going to consider the negative one and the positive one like that. So I have two rejection regions, this one and also this one here, okay? So if the calculated value that I'm going to find is going to fall in this region or that region, I'm going to reject the null hypothesis. So this region we reject. This region here we also what? Reject. And then here we fail to reject. Okay, don't say we accept, no. Just say fail to reject. All right, so what is the t statistics? The sample size is small. We don't know the population mean. We're using the t statistics. So t calculated is equals to sample mean minus population mean divided by, okay, divided by standard deviation over square root of n. So the sample mean is 11.2 minus the population 13.5 divided by the sample is 1.5. I mean the standard deviation divided by the sample size, the root of the sample size. So what am I going to find here? Okay, so let me punch this onto my calculator. Okay, so I'm finding minus 4.85. Okay, so this is the test statistics here. Okay, so then now let's find the critical value of this t. So remember our degrees of freedom is just n minus 1, which is equals to 10 minus 1, so it will be 9. And then the significant level that we were given, okay, remember it is 0.0 what? 1. Okay, it is 0.01. But now our regions have been divided into two. Okay, our regions have been divided into two. There's this region and this region. So it means we have to divide this guy by 2. Okay, so it means we are going to have what? When you divide this by 2, we're going to have 0.005 like this. Okay, we're going to divide it by 2. So I'm going to say now t of alpha divided by 2, and then the degrees of freedom n minus 1 is equals to t 0.005, comma 9. So let's find this value on our t table. Okay, so 0.005, comma 9. So if I go here on my t table, where can I find it? The 0.005. So the 0.005 is there. Okay, let me use red. Where are you, red? Okay, so this is the 0.05, and then I'm going to 9. So 9 is there. So I'm coming like that. Okay, so this is the value that I'm going to get. So that value is, okay, that value is 3.250. Okay, all right. So I'm going to write here plus or minus 3.250. Okay, so the minus, I'm going to put it here. Okay, so minus 3.250. Okay, so t will be equals to this at this point, then t will be equals to 3.250. So if this value that we found is either in this region or in this region, we are going to reject the null hypothesis. Okay, so what do we see? Okay, what do we see? We see that the t calculated, which is minus 4.85, is actually, okay, is actually less than minus 3.250. So what does this mean? We are going to reject the null hypothesis. Okay, so reject the null hypothesis and conclude that at significant level of 0.01, okay, there is sufficient evidence. Okay, there is sufficient evidence that the mean level differs from the the normal population mean. Okay, so that the mean level differs from the population mean. Okay, that's how we conclude there. So we are done with question 2. Let's look at another question, question 3. Okay, so question 3, they're saying in a plot to study 12 type 2 diabetics on diet Z, fasting blood glucose yields a mean sample of 150. So mean sample of 150 and standard deviation of 20. Okay, test at 0.05 significant level whether the diet fails to achieve the target mean of of 140. Okay, whether it fails to achieve the target mean of 140. Okay, so here they're saying what? In a plot to study 12 type 2 diabetics on that Z. Okay, fasting blood glucose yields a sample mean of 100 and what? And 50, with a standard deviation of 20. And then they're saying test at alpha is equals to 0.05 whether the diet, okay, fails to achieve the target mean of 100 and what? Of 140. Okay. Okay, so let's write the hypothesis. Okay, so the uh, the now hypothesis here will be that the mean is equals to what? To 140. Okay, so now take note here that we are testing against fasting blood sugar. Okay, so this statement here that says test whether the diet fails to achieve the target mean of this. Okay, so if it fails to achieve the target mean of this, it means the blood glucose, okay, its levels will be way higher. Okay, so it means the alternative hypothesis here is that the mean is greater than what? 140. So this is a one-tailed test. Okay, so if I draw my diagram like that, so it means we are considering this part here. Okay, so this part here is our rejection region. Okay, and then the rest here is fail to reject. Okay, so we are using the t-test, so the t-statistics will just be equals to sample mean minus population mean divided by standard deviation over the root of n. So the sample mean, it's 150 minus the population mean divided by 20 divided by the root of 12. Okay, so let me calculate this on my calculator. I'm getting 1.73. Okay, so what about the value uh, at the critical alpha there? Okay, so it will be T alpha and then the degrees of freedom. So N here is 12, so it means the degrees of freedom is just 11. Okay, so it will be T 0.05, comma 11. So why are we not dividing this? Because this is a one-tailed t-test. We just want to find this value here. So this value will be, okay, so we go back to our t-table here. Okay, so that was 0.05. Okay, so 0.05, it's somewhere there. And then we go to 11. So 11 will be somewhere there. So that is 1.796. Okay, so this will be 1.796. And since it's a right sided t-test, okay, this one remains the way it is, a positive value. So now we compare the calculated t to this t, okay, of these critical values here. Okay, so what do we see? We see that, okay, we see that the t calculated, which is 1.73, is actually less than 1.796. So if it's less, then where is it? Is it in the rejection region or they failed to reject? Okay. So if it's less than this value, then it's in this region here. And in this region, we are failing to reject. Okay. So failed to reject there. Okay, so our conclusion there will be, let's write it on top here. Okay, we're going to say since the t calculated, okay, is less than the t of the critical value, we failed to reject. Okay, we failed to reject the H, okay, and we conclude that at significant level of 0.05, okay, there is insufficient, okay, or not enough. There is insufficient or not enough evidence, okay, to conclude that the diet Z, okay, fails to meet the target, mean of 1/4. Okay, so that's how we're going to conclude there. Okay, let's look at our last question. Right, so our last question, they're saying what? Okay, so they're saying in 14, okay, in 14 emergence trauma cases, so 14 is a it's a sample size. A novel hemostatic agent yields mean time to hemostasis of 3.2. Okay, so the mean is 3.2 and the standard deviation is 0.8. Test at 0.05 whether this exceeds the clinical benchmark. Okay, so this one is very clear. So it means the null hypothesis there, okay, will be that the mean is equals to 2.5. And then the alternative, okay, they're saying exceeds here. So it's the mean should exceed the 2.5. Okay, so test statistics will be equals to sample mean minus population mean divided by standard deviation over the root of n. So the sample mean we've been given is 3.2 minus the population mean 2.5 divided by divided by the standard deviation, the root of n. So n is 14 now. So this is going to give me what? Okay. So this is going to give me 3.27. Okay. Okay, so this is the t calculated. Let's find the critical value. Okay, so t at the degrees of freedom is equals to. So this one here, since this one is greater than like that, it is a one-tailed test. Okay, so if I draw it like this, we are looking for this value of t. So this is the rejection region, and then this one is fail to reject. Okay, so let's calculate this. So it will be t 0.5, okay, comma, 14 minus 1, which is 13. So we're looking for this value now from the table, 0.0513. Okay, where is it now? So 0.05 is still this one, and then 13, it will be there. Okay, so this value here. So 1.771. Okay, so I'm right, 1.771. So this is the critical value here. Okay, so now we compare the critical value to the what? To the test statistics. So we see that the test statistics 3.27 is greater than the critical value there. Okay, it's greater than the critical value. So what does that mean? This calculated value, okay, it's somewhere after this t. Okay, so it's somewhere here. So it's in the rejection region. Okay, so since that is true, we are going to say, okay, we are going to say we reject the null hypothesis. Okay, so we reject HO, okay, and then we conclude that at significant level of 0.05, okay, there is strong or enough evidence, okay, that the mean time to hemostasis, okay, using the new agent exceeds the clinical benchmark. Okay, of 2.5 minutes. So that will be our conclusion there. Okay, and that's all for this video. Thank you so much for watching.